Today we're going to take a look at section 2.7, linear programming. And our linear programming is the application of everything from chapter 2 that we've been building up to. Why have we been graphing inequalities? Why have we been solving systems of equations? It's all to come to this application of it, which we'll call linear programming. So taking a look at this first problem, suppose a lumber mill can turn out 600 units of product each week. To meet the needs of its regular customers, the mill must produce 150 units of lumber and 225 units of plywood. If the profit for each unit of lumber is $30 and for plywood is $45, how many or each type of wood should the mill produce to maximize the profit? Now that's a lot of words in there, so we need to break this apart and see what we can use. The procedure for doing this is the first thing we want to do is define the variables. What are we asking for? What can change in the problem? Then we're going to write the constraints as inequalities, graph the constraints and find the vertices, write the expression to be maximized or minimized, and check each vertex. So we're using that vertex theorem from yesterday, but an actual real world application of this. So let's take a look at these constraints, and we'll go through our steps. Define the variables. Well, let's take a look back at example 1 and highlight what we have here. We can turn out 600 units of product each week. To meet the needs of its customers, the mill must produce 150 units of lumber and 225 units of plywood. If the profit for each unit of lumber is $30 and the plywood is $45, how much of each type of wood should the mill produce to maximize profit? So we can look at this in a couple ways. We can start looking backwards, and even though our last step was to write the expression to be maximized, we have it right there. We want to maximize profit. So I'm going to write that down. Maximize profit. Okay, so that's what we want. Now these variables, what can change? Well, in this mill, we have lumber and plywood. So let's let X equal lumber and Y equal the plywood. Well, to maximize that profit, we need to decide how much lumber to have. So our equation, the functions we want to maximize, is f of x, y, or that lumber and plywood, well, how much money can we make? Going back, we have $30 for lumber and $45 for plywood. So $30 for the lumber and $45 for the plywood. So here's what we want to maximize here. Now we have to come up with our inequalities. Well, we can turn out 600 units of product each week, so we can't have more than that. So our lumber plus our plywood has to be less than or equal to 600 units. Now our next two, we have to produce 150 units of lumber and we have to produce 225 of plywood. So our lumber has to be greater than or equal to 150 and our plywood has to be greater than or equal to 225. Now all we have to do is what we did yesterday. Let's graph this and see what we can come up with. Now, looking at our graph here, we can see that we have all 4 quadrants. But when we think about this, we're not going to make negative amount of lumber and plywood. So let's take this and we'll turn it into an L graph instead. And I'm going to have to cut off the bottom here. So we're not worrying about quadrants here. We have our X and our Y. Now looking at this, all of this, we can graph the bottom two, but this top one, we need to subtract the X. So this is really Y is less than or equal to 600 minus X. So to graph this, we have a y-intercept all the way of 600. So we need to decide what to count by. And maybe we want to count by 50s or 25s. Let's see if 25 would fit. 25, 50, 75, 100, 200, 300, That won't fit on here. So let's count by 50. So 50, 100, 200, 300, 400, 500, 600, and we can do the same over here. 100, 200, 300, 400, 500, 600. We'll see if that's far enough out. So our first equation here, I will put a box around this one. I'll do this in the dark color. 600 minus x. So we can go back here. Our y-intercept is 600, and our slope is -1. And since our x and y scale are the same, we can just say down 1 and over 1. That's really down 50 and over 50, but that's the same as 1 over 1. And we can continue this. Okay, and connect our line right here. Let's go back and take a look at our next one. I'll do this one in blue. X has to be greater than or equal to 150. Well, this is our x here, 150. Okay. And our last one, we'll do this one in red. Y has to be greater than or equal to 225. Let's see, 200, that's 250, so 225 is right in between here. And we can think about where we shade greater than 225, greater than the 150. And let's see, if we plugged in 0, 0 for this one, our test point. Yep, well that holds true. 0 is less than 600, so we would shade on bottom of our dark line here. So that means our solution area is right in here. So now we need to figure out those vertices. I'm going to write the equations on here before we forget those. X is 150. This is the equation. Y is 225. And this equation here is 600. Y equals 600 minus x. Now, some of these vertices we'll be able to tell. This one right here, that's just our blue line and the red line. So we know that is the coordinate 150 and 225. This next bottom one, though, that's a little bit more difficult to tell. It's the intersection, though, of our black line and our green line. So if we were to calculate that out, our black line is y equals 600 minus x. And we wanted the intersection with our red line, which is y equals 225. Well, we know our y value, but we can figure out what our x one is simply by plugging in our y value. So we know y is 225, so 225 equals 600 minus x. Subtract the 600, so we have negative 375 equals negative x. So that tells us that x is 375. So our coordinate for the second one, x is 375, y is 225. And then our third point of intersection up here, it is with the blue and the black line. So let's see, we have blue and black. And our equation is y equals 600 minus x. And this one was x equals 150. We'll plug in our x value. We know y is 600 minus 150, or y is 450. So our final coordinate is 150 and 450. Now what we have to do is actually maximize this and find out the maximum profit we can get. So let's go back. Our profit equation was f of xy equals 30x plus 45y. Now we have those coordinates, those intersection coordinates, so let's write those down. 150 and 225, 150 and 450, and 375 and 225. I believe that's what it was. Yep. So now all we have to do is plug these in. X is 150, Y is 45. So what is 30 times 150 plus 45 times 225? This next one, we have 30 times 150 plus 45 times 450. And the third one, 30 times 375 plus 45 times 225. So take a minute, plug those into your calculator, and let's see what we get. Let's see, I had a profit on this one, 14,625. We're making some more money here, 24,750. And 21,375. Now if we go back to our original problem, we want to know how many of each type of wood should the mill produce to maximize profit. Well, our X and Y, we should produce 30, and let's see what the label was. Lumber was our X value. Whoops. So going back here, excuse me, our X value, 150 units of, maximum right here. Looking at the wrong one. Here's our maximum. 150 units of lumber. 450 units of plywood, would give us our maximum earnings of 24,750. Now, not all our graphs will have overlaps. If there's no overlap, we say the problem is infeasible. And some will be unbounded, such as if we had a graph here, and let's say here's our lines right here, and the intersection is up here. That's unbounded. We could make, if it was a profit one, their profit could keep on growing. Overlap would be one that's infeasible, would be like yesterday's example 2. If you remember that graph, we had two parallel lines. I believe they were dashed yesterday, but we were shaded on the outside, so there was no solution. It was not a feasible option.